During part 2 of our look at Notes 15, we focused on this idea of our test statistic for an ANOVA test being calculated as the mean squares between divided by the mean squares within. And we said that those were looking at the average variability between our groups by comparing our sample means for each group to our overall sample mean. And then the mean squares within was done by looking at how spread out our data was within the specific groups. And where we ended was talking about this concept of, well, how do we actually compare these? What kind of information are we getting from this? So the first question we have here is, if the null hypothesis was true, would we expect the mean squares between groups to be large or small? And if you think about it, our null hypothesis said that all of our population means were the same. So if all of your population means are the same, you would expect that your sample means would likely be pretty close together as well. And so mean squares between should end up being small. On the other hand, if the alternative hypothesis is true, at least one of our population means is different from another, maybe more than one, maybe all of them. And so there's no reason that our sample means would necessarily have to be close to each other. So large mean squares between seems like it matches up more with our alternative hypothesis, and small mean squares between seems like it matches up more with our null hypothesis. But there's still the issue of what constitutes a large value and what constitutes a small value. And that's actually where the mean squares within really helps us out. So the mean squares within is essentially telling us if nothing was really going on at all, how much would our data just kind of vary naturally? So for the cereal box example, not every store is going to sell exactly the same number of cases of cereal, and so even if they were all using the same package design, there'd be some variability between the stores. And so when we randomly assign the stores to use, say, package design A or package design D, it's possible that, one design might have a slightly higher sample mean just because of this variability within groups. So when we look at how much our groups vary from one another, we're going to compare that to how much natural variability there would be if nothing was going on, and that's why the ANOVA is called the analysis of variance. If our groups are varying a lot more than what would happen if nothing was going on, that tells us that we think that there probably is something happening. The alternative hypothesis probably is true. So if you look at what this was for the cereal example, our mean squares between was 196, and our mean squares within was about 10.5. That actually tells us that there was about 19 times as much variability between the groups as there was within the groups. And that's a really strong indication to us that package design probably does matter, because these groups seem to be varying a lot more than we would expect if package design didn't matter at all. But we've seen that when we have a test statistic, it helps for us to know the sampling distribution for that test statistic. So again, what kind of values we would get if the null hypothesis was true. And then we can use that to find p-values and reach a conclusion that we feel really comfortable with. So the sampling distribution for an ANOVA test, because we are calculating a test statistic that we're calling an F statistic, this test statistic is going to follow what we call an F distribution. And there's some things about the F distribution that might seem a little familiar to you, and then there's some things that are a little bit different. So just like the t distribution and just like the chi-squared distribution, the F distribution depends on degrees of freedom. But the new thing with this distribution is that there's actually two different degrees of freedom. There's something that we call the numerator degrees of freedom, and we calculate that as the number of groups we have minus 1. So this is an I minus 1. And we also have what we call the denominator degrees of freedom, which is the overall sample size minus the number of groups. And if you go back to the mean squares between calculation, you'll actually notice that this I minus 1 was on the bottom of that calculation. And if you go back to the mean squares within calculation, you'll notice that this n minus I was on the bottom of that. And so that's where the numerator and denominator part is coming from. In terms of what the F distribution looks like, well, because it depends on the degrees of freedom, there's actually quite a few different shapes that this could take. But in general, the F distribution will usually be right skewed. So I put 3 different examples on here. This is an F distribution with 2 for the numerator degrees of freedom and 10 for the denominator. Here's one with 5 for the numerator degrees of freedom and 20 for the denominator. And here's 10 for both the numerator and denominator degrees of freedom. So you can see that sometimes, you start to see this little hump with just a long tail. Sometimes it just sort of slopes down like this. But we can use StatKey to generate these pictures, and we're going to use StatKey here in just a second to find p-values regardless of what our sampling distribution looks like. All right. So if we want to find a p-value for an ANOVA test, we are going to shade to the right. We saw this happen with chi-squared problems also, where we just said that if we get a big test statistic, that means that our variability between groups was a lot bigger than our variability within groups. Those are the types of results that are supporting our alternative model. So when we're assuming the null is true, we look at our sampling distribution, we put our test statistic on there somewhere, and then any test statistic bigger than ours would be even stronger support for the alternative hypothesis. And so that's how we're going to decide that we're always going to shade to the right of our test statistic when we're doing an ANOVA test. And so if you want to find a p-value using StatKey, like I said, a lot of this should be familiar. I'm going to go to StatKey and I'll select F distribution. I'm going to enter the numerator degrees of freedom and the denominator degrees of freedom when it asks me. I'm going to choose right tail because I said that I'm always shading to the right. And then I'm just going to find a number along the x-axis, change it to my test statistic, and I'll see that it's shading everything above that. So there's a couple problems here that you can try on your own. Make sure that you could get these same pictures if you went to StatKey. For the first one, we're assuming that our sampling distribution has 15 for the numerator degrees of freedom and 10 for the denominator degrees of freedom, and we're getting a p-value for a test statistic of 1.8. So I would enter F on the first page. I would put 15 and 10 for my 2 degrees of freedom. This picture would pop up. I would select right tail. I would enter 1.8 down here on the bottom, and this 0.175 is the shaded area. That would be my p-value. And you could do something similar for a test statistic of 4.1. But what I want to do is revisit our serial example, and let's do that problem for this one here. So I'm going to go to StatKey, and I'm going to choose F distribution, and it's going to ask me for my degrees of freedom. So let me go back here, and let's remind ourselves, for mean squares between, I've got I minus 1 down here on the bottom, which means my numerator degrees of freedom is going to be 3. All right? And then the denominator degrees of freedom is that part that's on the bottom of the mean squares within formula, n minus I. In this case, that's 19 minus 4. So I'm going to have 15 for my degrees of freedom. And that's what my distribution looks like. I know that I'm always going to choose right tail. And then I need to remind myself what my test statistic was. So right here, we calculated our test statistic to be 18.59. So I'll change this number to 18.59. And this should look sort of like what we saw on the second page of the notes when you did this randomization activity before we even knew what the F distribution was or what an ANOVA test was. What we saw was that if nothing was really going on, the vast majority of the time we would get test statistics down around here. And then the one that we actually got was way, 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 way out in the tail. And in fact, the p-value for this data would be 0.000026. So really, 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 really small. All right. And a lot of this is in the notes here. I'm going to scroll back to our example that we're working through. All right. So here's my test statistic. Here's how I found the degrees of freedom. That tells me what my sampling distribution is. And then I go do what we just did in StatKey. And even though you've never done an ANOVA test before, you've never written a conclusion for one, hopefully you'd have a rough idea of what this would look like. I would say something like, based on my p-value, which is much, much, much smaller than 0.05, that means that I have very strong evidence to conclude that at least one of my package designs has a different population mean sales than another. And that's based on the alternative hypothesis. So essentially, I'm doing what we've done all semester. I'm saying my p-value is small. That means I have sufficient evidence that my alternative hypothesis is true, and I just need to put it in context of the problem. So for the next part of our video, what we'll do is we'll look at how this information is usually arranged for you, particularly when we use SAS. We don't want to do all of these calculations by hand. So how is SAS going to give us this information so that we know how to work with it to answer these types of questions for other problems?